For this last piece of this section on implicit differentiation, we're going to explore the derivatives of the inverse trig functions. So let's take just a little minute here at the beginning to just talk about the inverse trig functions. So we'll look at the inverse sine of x, which can also be written, by the way, and some of you are more familiar with the arcsine of x, or the inverse cosine of x, or the arc cosine of x, or the inverse tangent of x, or the arc tangent of x. Those are just equivalent ways of writing the same thing. And I will move back and forth between those. They're both very commonly used ways to express the inverse trig functions, and so it's good that we're familiar with both ways to express those. So when we talk about these inverse trig functions, and actually before we can even define an inverse trig function, we have to think about what would be the restriction on the actual trig function to make it one-to-one, because you can't have an inverse function unless the function you're looking at is one-to-one, and the trig functions are not one-to-one. So let's pause here for a second and just go over to Desmos and explore sine and inverse sine of x a little bit closer in a graphical realm. Okay, so here we are in Desmos, and we have the sine curve. So this is clearly what I have dashed here is just the sine curve. I'm kind of moving it around, but we should be familiar with the sine curve. So I've graphed the sine curve, and in order to look at the inverse of a curve of a function, we have to have that function be one-to-one. Otherwise, the inverse doesn't exist. That's just the properties of inverses. We have to be able to move back and forth between a function and its inverse, between inputs and outputs, and switching our x's and our y's when we talk about inverse functions. So what we have to do for the trig functions is we have to restrict their domain. We have to say, you know what, let's only look at a piece of the sine curve or the cosine curve or the tangent curve, and then we can create the inverse function on that restricted piece of each of those trig functions. So the standard restriction for the sine curve, when we want to talk about inverses, is to restrict it from negative pi over 2 to pi over 2. So I'm going to go ahead and do that restriction so that we can see that on the curve, and you can see that now on sine of x. You can see that showing up in blue. And that little piece, notice, is one-to-one. Every input has just one output, and every output comes from just one input. That's the generalization for what makes it one-to-one. And so you can see this. Or you could also think visually it passes both the vertical line test, making it a function, and the horizontal line test, making it a one-to-one function, which will have an inverse. And so if we do that, if we make that restriction for x, make it from just negative pi over 2 to pi over 2, that will give us an inverse, and the inverse will be graphically the reflection across the line y equals x. So here we've got the graphical curve of arcsine of x, or inverse sine of x. And in fact, you know what, let me just change the color of that. Let's make that red so that it really stands out. There we go. So now you can see both the sine curve with its restricted domain from negative pi over 2 to pi over 2, and you can see the inverse sine curve here in red, and that is the inverse sine curve, and that's the curve that we're going to be looking at. Now remember, the other thing to note that I'm going to talk about when we flip over to the other screen, but while we're looking at this visual, when you have an inverse function, the inverse of a function has flip-flops domain and ranges, because we're doing a reflection across y equals x. So we're doing a reflection across y equals x, and so we're flip-flopping domains and ranges. That's going to come into play when we get over into looking at the derivatives, and so I want to just mention that here. So the restriction on the domain here for the sine of x is from negative pi over 2 to pi over 2, and the range, of course, for the sine of x is from negative 1 to 1. It covers the span of all of its values on that restricted domain, so it goes from negative 1 to 1. So what happens when we look at the actual inverse sine, those two switch. So the domain becomes the values between negative 1 and 1, and the range is the values between negative pi over 2 and pi over 2. The inverse sine function returns an angle for us, if you want to think of it that way too. Okay, so let's head back and let's actually find the derivative of this red function, this inverse sine curve. Okay, so let's come back in here and let's go ahead and find our derivative of the inverse sine of x. And to do that, I just grabbed that image that we were looking at over in Desmos and I labeled it over here. And so what you can see here is in red, we have our inverse sine of x. That's the derivative that we're looking for. You can see where it came from. It came from the restricted domain on the sine of x, y equals the sine of x in blue here, where x is only between negative pi over 2 and pi over 2, versus the dashed line, which was in gold there, which was our full sine of x curve. And so just down below here, I also just labeled some things here. What we're doing is we're taking the sine curve, but with a restricted domain. So here's that restricted domain that allows us to have a one-to-one curve. So that allows the sine of x. That makes the sine of x 1-to-1, which allows it to have an inverse. So it makes sine of x a 1-to-1 function when we restrict the domain like that. So that makes sine of x 1-to-1. That's why it's a restricted domain. And then it does have an inverse, and its inverse we call the inverse sine of x, or arcsin of x, and it will have a domain from negative 1-to-1 and a range from negative pi over 2 to pi over 2. Okay, that will become important as we go through the derivative. All right, so let's do it. So if I want to find the derivative of this, and I know nothing about the derivatives of the inverse sine curves, how am I going to do this? Well, what we could do is we could use inverse properties first. So let's use the inverse properties. So we're going to go through a little proof here, and let's use the inverse properties. And just actually say if y equals the inverse sine of x, then the sine of y has to be equal to x. So we just use inverse properties. And then I say, well, I do actually know the derivative of the sine of y, and I know implicit differentiation. So now let's apply implicit differentiation to both sides. So now let's just take the derivative of both sides of this equation with respect to x. Now remember, when we do implicit differentiation, we're thinking of y as a function of x, which it is, right? It's right up here. Y is a function of x. It's the inverse sine of x. And we'll take the derivative of the other side, which is x. So whenever we take the derivative, we have to use our proper derivative rules. And right here we have the sine of y. So that's a composition, right? The y value, the y as a function of x has been composed inside of a sine function. So we'll take the derivative, which is the cosine of y, but then we have to multiply by dy dx. So just using our implicit differentiation process here, take the derivative of x on the other side, which is just 1, and then solve for our dy dx. So dy dx is actually equal to 1 over the cosine of y. And so we have implicitly found the derivative right here. So we have actually found the derivative, but it's in terms of y, and we can do better. So now what we're going to do is we're actually going to use the relationships with trig functions to write this explicitly. To write dy dx explicitly in terms of x. Because once we have a formula, then we can use that formula, just like we've used formulas in the past for functions once we figure out what their derivatives are. So we can write dy dx explicitly in terms of x. So now we're going to go through and we're going to do a little bit of work. So I know this. I know that the derivative of the inverse sine is 1 over the cosine of y, but I want to get that back in terms of x. So how am I going to do that? Well, I know this. I know that the sine squared of anything, so the sine squared of y, there's actually a couple ways to do this. I'm going to go first with just identities. And the cosine squared of y, the sine squared plus the cosine squared is equal to 1. So that means that the cosine squared of y has to be 1 minus the sine squared of y. And then I could take the square root, and the cosine of y has to be equal to plus or minus the square root of 1 minus the sine squared of y. Now, why would I do that? Well, we know, little note right here, if I could go back to where we started, we know that the sine of y is equal to x. So if I can get cosine of y in terms of sine of y, then I would be able to do a replacement where, let's make this note, where the sine of y is actually equal to x. Okay? So we'll come back to that in just a second. I'm going to replace this with x squared, but I want to talk about this part right here, this plus and this minus right here. And let's go back up to our definition right here. Luckily it's still on the screen. So let's go back to the domain. I said that this would come back into play, and here's where it's going to come into play. If y equals the inverse sine of x, we can't even have an inverse sine of x unless we've had a restriction on the original on the sine of x. And so doing that creates this domain and range for the inverse sine of y. The domain is from -1 to 1, but the range, which is a little more important because range is where our y values come from. So y comes from the range. Our y values are from -π/2 to π/2. So the cosine, so let's think about the cosine of y here for a second. The cosine of y, where y is between, remember, y is between -π/2 and π/2. So if y has to be between, let's put it as actually as an inequality, between -π/2 and π/2. That looks a little funny because y is actually going to be on the what we would normally think of as our x-axis, the horizontal axis, but we're defining cosine of y here. So if the cosine of y, where y is between -π/2 and π/2, think about actually graphing that. Or if it's easier for you, think about the unit circle. Think about your angle being between -π/2 and π/2, and think about the actual sine of the cosine of those angles. I'm going to a graphical approach here, but you could definitely use a unit circle approach. If we were to graph the cosine right here, it would be this, it's kind of flattened out, but you can see it. This is the rest of it. But it's this part right here where it's above the x-axis. It's always positive. So the cosine of y is greater than or equal to 0 when, let me make that, I had to squeeze that in there. It's greater than or equal to 0 when y is between -π/2 and π/2. If it is easier for you to think on the unit circle, think on the unit circle. And just think about when your angle is between -π/2 to π/2, so it's in quadrant 4 or quadrant 1, that your cosine is going to be a positive value. Your cosine values are going to be positive. And so what we can say right here is we can say that the cosine of y has to equal the positive square root of 1 minus the sine squared of y, since y, which we know, is in the range from -π/2 to π/2. Okay, so this is, I didn't write a positive here, but let's put a positive there. Okay, it is definitely a positive. But we have to talk about that because when you take a square root, you end up with both a positive and a negative root. And so you can't just gloss over that. You have to talk about that. You have to justify why that would be positive. And it will be positive here. So the cosine is going to be equal to a positive square root of 1 minus sine squared. We already talked about how the sine squared of y is equal to x. I didn't do that. I didn't actually replace that there, but I could have. So the cosine of y, it turns out, is simply 1 minus x squared. Well, that is very convenient because remember, our whole goal here is to try to write this derivative explicitly in terms of x. And so we can come back up here right where I put this star right here, and we can say, look at this. This is actually equal to simply 1 over the square root of 1 minus x squared. We can write that explicitly. I'm going to put a star back on it again just to remind us where that came from. That came from down here. Okay, we just did that. We just figured that out through this work, through that identity. I just used a Pythagorean identity actually, but we had to also think about the restriction on y, that y is between -π/2 and π/2. Okay, so we have a derivative. It turns out that the derivative of the inverse sine is actually, let's get all the way back up here. Let's get it all on one screen if we can. The derivative of the inverse sine of x is actually 1 over the square root of 1 minus x squared. And I'm going to write that up in just a second, but I wanted to mention one other thing here. Down here where we went to this identity, so right here where we went to this identity in this little piece right here, I mentioned the unit circle and how you could be visualizing on the unit circle. I wanted to just mention one other thing as well. It turns out that the sine of y, so if we could focus on this part, which is actually up above, but I'm going to rewrite it down here. So I'm just going to say or, another approach. Okay, so here's another approach to rewriting. If we end up with dy dx, another approach to rewriting dy dx 1 over the cosine of y. Another approach would be to say, where we know that the sine of y equals x. Another approach, and some people like this better, uses more of the right triangle trigonometry rather than in the unit circle. Well, I mean, it kind of uses both. What we can do is we can say, well, if the sine of an angle is equal to x, then what that means is that opposite over hypotenuse, I could draw a triangle. I could draw a reference triangle with angles labeled, or with sides labeled x and 1 for the opposite and the hypotenuse. Now, that said, where does that y come from? Well, we've talked about this at length now. That y is coming from negative, somewhere in between negative pi over 2 and pi over 2. So the triangle, the reference triangle that we're going to be drawing here is going to be somewhere in the, from negative pi over 2 to pi over 2. So it's either in the fourth quadrant or in the first quadrant. And so I'm going to draw it in the first quadrant. I'm going to draw in my right triangle here. Here's my angle y. This is the opposite side labeled x. This is the hypotenuse labeled 1. And this side would be 1 minus x squared. Simply using Pythagorean theorem right there. So I jumped to that. It was not magic. I was just doing the Pythagorean theorem in my head, knowing that this is the hypotenuse, which is 1 squared minus x squared, and then taking the square root to get that missing leg of that triangle. Now, you do get a plus or a minus, right? When you come up with this missing leg right here, you come up with a plus or a minus. You get plus or minus the square root of 1 minus x squared. But again, we have to be in either of these two quadrants where this leg of the triangle is positive. And so we would take the positive root. So I did all of that kind of in my head just to speed this up a little. But that is what I was doing right there. Now, what is the cosine of this angle? Well, the cosine of this angle is simply the adjacent over the hypotenuse. So it's simply 1 minus x squared over 1, or the cosine of y is simply the square root of 1 minus x squared. And we can come over here and plug that in. It's 1 over the square root of 1 minus x squared. And so notice both here and in my first approach, I got to the same thing. Okay, so that was a lot of pulling from our knowledge of trig and utilizing identities and reference triangles and graphs of trig functions. So what the goal was here, though, was to determine what the derivative of the inverse sine function was. And what we have shown is this, that the derivative of the inverse sine of x, or the arcsin if we want to say arcsin, is equal to 1 over the square root of 1 minus x squared. And that we can utilize when we're taking derivatives. We can do the same exact process to come up with the formulas for the derivative of the inverse cosine, the inverse tangent, the inverse secant, the inverse cosecant, and the inverse cotangent. And they will all depend on the restrictions because, again, all of them are functions that are not one-to-one, unless we put a restriction on the domain. But as soon as we do a restriction on the domain, it allows us to both have an inverse function and be able to find the derivative of that inverse function. And so we do have all 6 of them. I'm going to leave the others as exercises, either in homework or on the worksheet for you guys to practice, but I'm going to go ahead, because they are good. It's good to practice these and think about what those restrictions need to be. But I'm going to go ahead and project the 6 formulas for the derivatives of the inverse trig functions. Okay, so here are all 6 of them. Similar proofs could be done. The ones that we are going to utilize over and over and throughout the rest of your calculus career are the inverse sine. Notice that the inverse sine and the inverse cosine are very, very similar. They just vary by a negative. So we will work with the inverse sine and the inverse tangent the most, but all 6 of these are derivatives that you need to know. You'll want to memorize these, put them on flashcards, whatever works for you, but get these 6 derivatives memorized. Oh, I do just want to mention that the derivatives for cosecant, secant, cotangent have some variations in different books, and it depends on how you define the original function, secant, cosecant, cotangent, and the restrictions that you make to allow for these particular formulas. So these are the ones that our book uses, but there are some variations, and sometimes you'll see an absolute value in them. But our book does use these 6 formulas. So again, I've left these up on the screen, screenshot it, write them down, whatever you need to do, but these derivatives you're going to need to know, and we're going to follow up with some examples using these now, but make sure you've got these guys down. Now let's use those derivatives, the sign that we just derived and the others that were stated in the table, to find some derivatives. So here we go. We got a function. It's defined as the inverse sine of 7x. So one thing just to note, right, I know the derivative now of the inverse sine, but I also notice that this is composed, right? This is a composition, and my inner function is that 7x. So keeping this in mind, and I'm just going to rewrite it here because we haven't used it all that much, so we might as well have it to reference right here off to the side until we get very familiar with these, right? Until we have these memorized. We'll write them lots of times, say them, flashcards, whatever works. But the derivative of the inverse sine of x, which we just proved, is equal to 1 over the square root of 1 minus x squared. Now, here we're not taking just the derivative of the inverse sine, though we're taking the derivative of the inverse sine of 7x. So my input here, my inner function is 7x, so that's going to get replaced in the derivative. So the derivative is going to be 1 over the square root of 1 minus the quantity 7x squared, and then I have to use the chain rule, and I have to take the derivative of 7x. Now, the derivative of 7x, and I'm just writing out all the steps here, but we would probably normally jump right here. The derivative of 7x is just 7. So this is 1 minus 49x squared times 7, or 7 over the square root of 1 minus 49x squared, and that is my derivative. Okay, I had to apply a little chain rule, not too complicated of a chain rule, but a little chain rule right there, and our derivative of our inverse sine. So there's our first example of just utilizing the derivative formula for the inverse sine that we just proved. So let's do another one. So let's take the derivative of x squared times inverse tangent of 3x. And again, I am going to just go ahead and write the formula for the derivative over here so we have it for reference for the inverse tan or the arctan. And that derivative, and it can be proved just like we proved earlier in the video for the inverse sine. It can be improved using implicit differentiation and then the relationship between trig functions, or drawing a triangle if you prefer that method. Okay? And that is a good exercise. You should try to prove this on your own. So let's check this out. So the derivative of this function, we're going to have to utilize product rule because we have a product. So we definitely have a product. So we'll remember we got to apply the product rule here. And in the midst of the product rule, when I take the derivative of the second function, I'm going to have to utilize my formula here for the derivative of the inverse tangent, and I'm going to have to think about chain rule and inner and outer functions because I have an inner function within the inverse tangent. So lots of things to think about here as we go through. So the derivative of this function, this is my first function, so this will be 2x times the second function, inverse tangent of 3x, plus, and then I have to take the derivative of the inverse tangent. So the derivative of the inverse tangent is going to be 1 over 1 plus 3x squared, because we're taking the inverse tangent of 3x. Then I have to multiply by the derivative of 3x, and I'm going to go ahead and just take that derivative right here. I'm going to simplify the steps here. So that's going to be 3. Then I have to multiply by x squared to finish out my product rule. So to multiply by f. So we've got g prime times f here. Let's put this in parentheses. There we go. Okay. All right, now we've taken the derivative, and I don't know about much simplification, but we could definitely rewrite that last line as 3x squared over 1 plus 9x squared, and there's my derivative. Utilizing that formula for the derivative of the arctan or the inverse tan. While I still have the formula for the inverse tan up on the upper corner of the screen, let's do one more utilizing that formula. Let's do another derivative that has an inverse tan or an arctan. So again, remember, arctan is the same thing as inverse tan, and we should get pretty familiar with either of these two notations for inverse trig functions. So the arctan of e to the 5x. Now this is multiple layers of chain rule. So again, as we do these derivatives, we're continuing to practice all of the rules and all of the formulas that we've derived up to this point. And so here we just have chain rule, and we just have to work our way through the chain rule. And so the derivative here is going to be, we're going to take the derivative of the arctan first, but remember that is going to be equal to 1 over 1 plus x squared, or 1 plus whatever the argument is squared. And in this case, it's e to the 5x. So the derivative here is dy dx is going to be equal to 1 over 1 plus e to the 5x quantity squared. Then we have to multiply. Now we have to peel away the layers through chain rule. So now we have to multiply by the derivative of e to the 5x. Well, the derivative of e to the 5x is just e to the 5x times the derivative of 5x, and the derivative of 5x is 5. And so our derivative here will become 5e to the 5x over 1 plus, when I raise a power to a power here, we multiply, so this is e to the 10x to simplify. And there's our derivative of the arctan of e to the 5x. Okay, let's maybe do one more here. Okay, so one last example in this video. Let's find not just a derivative, but let's find the slope of a tangent line to a curve at a specific point. And so again, we've done loads of these, right? When we want the slope of a tangent line, or even if we'd wanted the full equation of a tangent line, we have to start by finding the slope. And the slope of the tangent line is going to be the derivative evaluated at 2 root 3. So in order to find that, I have to first find the derivative. So let's find f prime of x. So to find f prime of x, we're going to have to take the derivative of this product, and it's a product, x times the inverse tangent of x over 2. So we'll have to apply product rule. We're also going to need to utilize, again, that formula for the derivative of the inverse tangent, which is 1 over 1 plus x squared. So as we're getting used to these formulas, I'll just rewrite them here so we have those for reference. So we'll take the derivative. So to take the derivative, we're applying the product rule. So we take the derivative of the first function, the derivative of x is 1, times the inverse tangent of x over 2, plus now we have to take the derivative of the inverse tangent. So the derivative of the inverse tangent, and again, it has a composition as well, the derivative of the inverse tangent is going to be 1 over 1 plus whatever the argument is there, which is x over 2 quantity squared. Okay? Then we have to take the derivative of x over 2. Well, just real quick, I just want to mention that the derivative of x over 2 is going to be 1/2, because x over 2 is the same as just 1/2 times x. So little note right there. X over 2 is just 1/2 x. So the derivative, I'm going to erase that actually because I'm going to run into it, but just as a note, that's what I'm doing here. The derivative of x over 2 is simply 1/2. Okay? So then I multiply by, using chain rule here, I multiply by 1/2. Then I multiply by x, because I've got, this is my g prime times f. So I also have to multiply by f in my product rule. So finishing out my product rule there. And let's see, let's just simplify a little bit, not a whole lot to simplify here. Oh, actually we could clean this up, this compound fraction we're ending up with over here. We've got x over 2, 1 plus x squared over 4, and I think I do because I got to plug something into this. So let's definitely, I'm noticing here if I were to multiply the top and the bottom of this guy by 4, that's going to clean up my derivative enough that makes it worth doing, especially since I'm going to be plugging in a value. So we end up with 4 plus x squared on the bottom and 2x on the top. And I like that. That looks like a nice cleaned up derivative. Okay, so there's my derivative. So now I want the slope at 2 root 3. So now I just have to plug in 2 root 3. So we'll plug in 2 root 3. So we're taking the inverse tangent of 2 root 3 over 2. So we'll be looking at the inverse tangent of root 3. Plus, now we got 2 times 2 root 3 over 4 plus 2 root 3 squared. And let's simplify that. So we're looking at the inverse tangent of root 3, and the inverse tangent of root 3 is going to be pi over 3. Again, remember we've restricted the domain. In order to even have an inverse tangent, we've restricted the domain. So the output values, the angle that would have an inverse, that would have a tangent of root 3 has to be pi over 3. So this is pi over 3 plus, and then let's see, what do we end up with here? 4 root 3 over 4 plus 4 times 3. And so that's going to be 4 plus 12. So we end up with pi over 3 plus 4 root 3 over 16. Oh, we can keep going. So that's pi over 3 plus root 3 over 4. And that's good enough for our slope. If we wanted a common denominator, it would be 12. And so we'd have 4 pi plus 3 root 3 over 12 if we wanted to take it that step further. And that's really up to you. Either of those is fine. And there's our derivative. Okay, our derivative up above using derivative of inverse tan, and our slope after plugging in 2 root 3. Okay, I'm going to end there with the examples, but we could definitely keep going with more examples and practice, but really getting used to these formulas and then applying our other rules, our product, quotient, chain rule, now adding in the inverse trig functions as an option for functions that we can work with and find derivatives.